In this video, let us learn about graph coloring and chromatic number of a graph. Graph coloring means coloring graph components. I may cover vertex, I may color edges, or I may color even the region also. So when we say graph coloring, we usually go for vertex coloring. Means we are coloring the vertices of a graph, but in some manner, not randomly giving colors to the vertices. With some manner we are coloring the vertices. So for that we say proper coloring. Proper coloring. It means painting all the vertices of a graph with colors in such a way that no two adjacent vertices have the same color. I mean to say, if I have this as my graph and I'm going to color this vertex, say, with orange, then these two are the vertices which are adjacent to this. I should not give orange color to these two vertices. I can give, say, blue. Here I can give blue, green, or whatever. Okay. Here again this vertex is not adjacent to this and I can give orange to this. Okay. So this is nothing but proper coloring. No two adjacent vertices should get the same color. Painting all the vertices of a graph with colors such that no two adjacent vertices have the same color is called proper coloring of a graph. In fact, we are doing vertex coloring. A graph in which every vertex has been assigned a color according to this proper coloring is called properly colored graph. Say I can color this in different ways. If I take same graph, here I can give orange, here I can give say black, I can give red, green, or the other way I can change it. In many ways I can properly color the graph. Just the thing is, no two adjacent vertices should get the same color. Now what do you mean by chromatic number? It's nothing but the minimum number of colors I'm using for proper coloring of a graph. See, when I take this graph G1, I have used only two colors, orange and say black. Okay, I have used only two colors in this. Here I have used orange, black, green, red. This is also properly colored but with the maximum number of colors. This is also properly colored with only two colors, means minimum possible colors I have used. Okay, this is now properly colored with the minimum number of colors, that is only two. So that is nothing but the chromatic number. Chromatic number is minimum number of colors used for proper coloring of a graph. When I consider this graph, it is properly colored with two colors. A graph G that requires K different colors for its proper coloring and no less of this K colors is called chromatic number, and number K is chromatic number is denoted by K. While coloring the graph, please note these things. We do not consider the disconnected graphs because when I consider disconnected graph, then coloring of one component will not affect coloring of the other. So we consider only connected graphs for coloring problem. And if I have all parallel edges between two vertices, that can be replaced by a single edge without affecting the adjacency. Okay, and the graphs should not have self loops Hence coloring problem is need to consider only for the simple and connected graph. Coloring problem is applied only for simple and connected graphs. A graph consisting of only isolated vertex. If the graph has only isolated vertex, then it is one chromatic. Means it can be colored with single color. So it's one chromatic. And if I have a graph with more than one edges, it is at least two chromatic. Remember, graph without self loop. Okay. If a graph has an edge, one or more edges, of course without self loops, is at least two chromatic. And if I have a complete graph, with n vertices, then it is n chromatic. Means minimum number of colors required to properly color the complete graph is nothing but the number of vertices in the graph, because in complete graph there is an edge between every pair of vertices. Therefore I need minimum n colors to color the complete graph. Therefore complete graph on n vertices is n chromatic. And the graph consisting of simply one circuit with say one cycle with the number of vertices greater than or equal to 3 is two chromatic if this n is even, and this will be 3 chromatic if n is odd, where n is number of vertices. Okay, these things I'll explain with an example now. These 3 points. See, if I have if I have an vertex, an isolated vertex, if I can use only one color to this. One color, say green. Okay, so isolated vertex is one chromatic. Now if I have two vertices and one edge, if I have, okay, then proper coloring means I should not give same colors to these vertices. So for this, if I give red, then for this I'm giving black. Okay, two colors are required if I have one edge. This is now two chromatic. Remark says a graph with one or more edges, then it is at least two chromatic. Okay, one or more. Now I had one edge. Now if I have two edges, now if I give red, black, then here I can give only red. Okay, for finding chromatic number I'm saying proper coloring means I can give any color to this, but to find the chromatic number I need to use minimum number of colors. So I can give red, so this will be again two chromatic. So that's the remark. A graph with one or more edges without self loop is at least two chromatic. Minimum number of colors required to color the graph with one or more edges is 2. Okay, now if I have a complete graph, say suppose complete graph on 4 vertices. Okay, this is my complete graph. Now if I color this with color 1, or I can say red. Then here I cannot give red, here I cannot give red, and even for this I cannot give. So I'll choose some other color, say blue. Okay, here I have given blue, so I cannot give blue over here, I cannot give blue over here. So let me choose some more color, some other color, say green. Now here again I cannot give red because it is adjacent to this. I cannot give green because it is adjacent to this. Cannot give black, it is adjacent to this. So let me give yellow. So how many colors I have used now? 4 colors. Therefore it is 4 chromatic. Since it's a complete graph on 4 vertices, I need minimum 4 colors to properly color this. Therefore that's the remark. If I have a n complete graph on n vertices, then that will be n chromatic. Means minimum number of colors to color complete graph on n vertices is n. Then if I see, you can think even if I have a triangle now, okay, this is the case which is helpful everywhere when you have to find the chromatic number of different graphs. If I have a triangle, I have given color red to this, black to this, cannot give red and black, so let me give yellow for this. Now every graph, this will be the trichromatic graph, so every graph having a triangle is at least 3 chromatic. Remember this thing, if I have a graph which has a triangle, then it must be at least 3 chromatic. Okay, at least 3 chromatic. It may be 3 chromatic. Okay, if I have only this, then I can say it's 3 chromatic. So the thing is, any graph, if it contains a triangle, then it will be at least 3 chromatic. Remember. So a graph consisting of simply one circuit with n greater than or equal to 3, where n is number of vertices, is 3 chromatic if n is odd. You can see if n equal to 3, then it's odd number. We have seen it is 3 chromatic. If n is 4, like this, n is an even number, then it is 2 chromatic. So I can give this example. I had already given this, right? Red, black, red, black, so that it will be 2 chromatic. So remember this thing, a graph consisting of simply one circuit, okay, with n greater than or equal to 3 is 2 chromatic if n is an even number, and if n is odd, then it is 3 chromatic because it will contain a triangle. Okay, now let us look at what is the chromatic number for a tree. Every tree with 2 or more vertices is always 2 chromatic. Tree is always 2 chromatic because see, when I look at tree, I have this. See, this is my tree, suppose. These are my vertices. Now select any vertex in any vertex V in this given tree. Okay, it's a rooted tree with more than 2 or 3 vertices I'm considering. Okay, this is the root. Suppose I'll start from this. Okay, this is a vertex V, which is a root. Now paint this root with color 1. Say one color I'm using color 1. Now color all those vertices which is adjacent to V with color 2, second color. Okay, you can choose the color or name the color by 1, 2, 3 like that. Okay, let me take color. Say I had taken red for this root and color those vertices which is adjacent to root with the second color. Say orange. Only 2 vertices are there which is adjacent to root. Okay, now you take all those vertices which are adjacent to these 2 vertices. Okay, there is no vertex which is adjacent to this. For this I have 3. Okay, color them with the first color, that is red, and go for the next step. Take those vertices which are adjacent to these vertices. I have these. So color them with the second color, that is orange. Like that, you continue this process until you color all the vertices of a graph. So in this tree, now we can find that all the vertices at odd distance from V have the second color, right? All the vertices which are at odd distance means distance 1, 3, like that, they have the second color. So this vertex, they are at odd distance, so they have second color, and these vertices are at odd distance and they have the second color, and all those vertices which are at even distance from B, they are colored with first color. So all the vertices have been colored with only two colors. Since I know that there exists only one path between any two vertices in a tree, and no two adjacent vertices have the same color, therefore I can say that tree is always two chromatic. Very important note, every tree with n greater than or equal to 2 is two chromatic. But remember one thing, converse is not true. I cannot say every two chromatic graph is tree. Okay, converse is not true. Because see, if I take any graph, say which is two chromatic, this graph is two chromatic, but it is not tree. This is not tree, right? So every tree with n greater than or equal to 2 is two chromatic, but every two chromatic graph need not be a tree. Now let us look at one theorem. A graph with at least one edge is two chromatic if and only if it has no cycles of odd length. Let us prove this. Let me take a connected graph G with circuits of only even lengths. Okay. Connected graph with cycles of only even length. Means it has no cycles of odd length, that means cycles of even length only. Okay, let me take the second part first, then I have to show that it is two chromatic. Okay, now consider a spanning tree of G, spanning tree T of this graph G. Okay, I'll properly, since it's a tree, I can properly color it with two colors. Okay, now for this spanning tree, I'm going to add chords one by one. Okay, since G has no circuits of odd lengths, okay, the end vertices of each chord, when I add these, each vertex in the chord will get different colors, because when I have a graph, for example, suppose I have a graph G with circuits of even length only. Okay, now in this case, this is my graph G. I'll write a spanning tree for this. Say Okay, this is my spanning tree. One chord is this and another chord is this. Okay, so when in this case, for the spanning tree, I'm going to add a chord. Okay, the thing which I'm saying is this end vertices of this chord will get two different colors because the graph has all the cycles which are of even length. So the color which I have used here will not be there on this point because this color will be there here. I have the graph with all the cycles of even length. So the chord which I am adding to spanning tree will have the end vertices with different colors. So I can say that G is colored with two colors with no two adjacent vertices having the same color. Therefore, I can say G is two chromatic. I repeat, I have graph G. I'm taking graph G with cycles of only even length. I'm taking its spanning tree. I'll color it with two colors because it's a tree. Then, since G has no circuits of odd lengths, the chords which I'm adding to spanning tree will have the end vertices are of different colors. So I can say G is colored with two colors and no two adjacent vertices will have the same color. Therefore, I can say that G is two chromatic. The second part is over. Converse part is if G has circuits of odd length, then we need at least three colors for proper coloring of a circuit. At least odd length means it will have a triangle. Okay, when I have a triangle, then I need minimum three colors to color the graph. Therefore, if G has cycles of odd length, the minimum possibility is having a triangle, right? We need at least three colors for proper coloring. Therefore, G cannot be two chromatic. I repeat the second part. See, first part I had taken cycles of even length. No cycles of odd length means cycles of even length, and I have proved it is two chromatic. Then the converse part I have to prove. I'll take two chromatic and I have to prove that no cycles of odd length. That is same as taking contrapositive of this statement. If G has cycles of odd length, then it cannot be two chromatic. Okay, the second part I had taken the contrapositive of the statement. That's what I had taken G as cycles of odd length. Okay, and I'm proving it cannot be two chromatic.